So according to Faraday's law of electromagnetic induction, so when a moving conductor is placed inside a magnetic field, so according to Faraday's law of electromagnetic induction, so when a moving conductor is placed inside a magnetic field, so a current will be induced in it. Okay. So if the conductor is forcefully moved inside the magnetic field, if the conductor is forcefully moved inside the magnetic field, so there will be a relationship between the direction of applied force, magnetic field and the current. Okay, so this relationship between these three directions is determined by Fleming's right hand rule. Okay, so here we have Fleming's right hand rule. So this is our right hand. Okay, so assume that this one is a right hand. So here we have the fingers, 5 fingers. Okay, so here this one is the thumb, forefinger and ring, middle finger. Okay, this one is the thumb, this one is the forefinger and this one is the middle finger. So here the forefinger, so this one. So the forefinger indicates magnetic field direction. So it will indicate the magnetic field direction, middle finger. So this middle finger indicates current direction. Okay, current direction. And the last one, that is the thumb. So the thumb indicates motion of the conductor. Okay, motion of the conductor. So this is the Fleming's right hand rule, which we use to give the relationship between current, magnetic field and EMF. Okay, current, magnetic field and applied force. Okay, to give the relationship between those three, we are using this Fleming's right hand rule. Okay, so here we have Fleming's right and left hand rule. So that one is used for the DC motors. Okay, Fleming's left hand rule is also there, but that rule is used for the working principle of DC motors. Okay, so next one is the basic working principle of DC generator. So here we have two poles, that is north pole and south pole. Okay, here we have two poles, that is one is north pole and another one is south pole. North pole and south pole. Here we have, these are the slip rings. So this one is the conductor. So this conductor is moved. This conductor has four sides, that is AB and ABCD. Okay, this conductor has four sides, that is ABCD. Okay, whenever these lines are, these horizontal lines are the magnetic flux lines. Okay, whenever the conductor is placed in the between two poles, here one magnetic field is occurred. So if the conductor is moved, the magnetic lines are cutted. Okay, these are the magnetic lines, flux lines. So these flux lines are cutted whenever the conductor is moved. So and here the conductor end is connected to the slip rings. So these are the slip rings we are using, and this is the brush. So this one is the brush and these are connected to the external load. This one is the external load. We have here we have the one resistor symbol. So this one is the called as an external load. Okay, external load. So that is the external load. This arrow mark gives the current flow direction or EMF flows direction. Okay. So coming into the working principle of DC generator, carefully listen. This one is the very important concept in this chapter. Working principle of this one. So here we have one coil or conductor. This one. Okay. This one is a coil or conductor. It consists of four sides, that is ABCD. So let us consider a single conductor rotated on a shaft within a uniform magnetic field. Okay, rotated on a shaft. So it is rotated in an anti-clockwise direction. Okay, so assume that it is rotated in a anti-clockwise direction. So here, when the coil sides AB and CD, so this one, when the coil sides AB and CD are moving parallel to the magnetic field, so this direction, so parallel to the magnetic field. Here the flux lines are not being cut. Here the flux lines are not being cut and no EMF is induced in the coil. Okay. So when the coil sides AB and CD, so this one AB and CD are moving parallel to the magnetic field, here the flux lines are not being cut because the conductor is moving parallel to the magnetic field. So in that way the flux lines are not being cut and no EMF is induced in the coil. Here the flux lines are not being cut and no EMF is induced in the coil. So at this position we assume the angle of rotation theta as 0 because there is no flux lines are cutted. Okay, that means no EMF is induced in the coil. Okay, at this position we assume the angle of rotation theta is 0. Okay, so this vertical portion of the coil is starting portion. So this is the starting portion. So according to Faraday's laws, the EMF induced is proportional to the rate of change of flux linkages. The EMF induced is proportional to the rate of change of flux linkages. Here we have two laws. Okay, so the DC generator working principle is based on Faraday's law of electromagnetic induction. Here we have two Faraday's laws. First law is whenever a conductor cuts magnetic flux. So whenever a conductor cuts magnetic flux, an EMF is induced in the conductor. Okay, that is the first law. And coming to second law, when a flux linking in the coil changes, an EMF induced in it. So when a flux linking in the coil changes, an EMF induced in it. Okay, that is the second law. Next, here the following are the basic requirements to be satisfied for generation of EMF. One is uniform magnetic field, another one is a system of conductors, and another one is relative motion between the magnetic field and conductor. Relative motion between the magnetic field and conductors. Okay, so here the one magnetic field. So here the magnetic field is a permanent magnet or electromagnet, that is nothing but a pole. Okay, and conductor. Here we are using copper or aluminum bars, and relative motion, that is by prime mover or turbine. Okay, these are the basic requirements to be satisfied for generation of EMF. One is magnetic field, another one is a conductor, and another one is relative motion between magnetic field and conductors. So already I said that this one. So when the coil sides AB and CD, so this one. So here, whenever the coil sides AB and CD are moving parallel to the magnetic field, this side, so this is the magnetic field, N and S. These are the poles or magnets we are using in this case. So this coil sides of the conductor is moving anti-clockwise direction and moving parallel to the magnetic field. So at that condition the flux lines are not being cut and no EMF is induced in the coil. So at this position we assume the angle of rotation is, that is theta is 0. Okay, so according to Faraday's laws here, so according to Faraday's law 2, that is, what is the Faraday's law 2 here? So when a flux linking in the coil changes, an EMF induced in it. So when a coil linking in the coil, when a flux linking in the coil changes, an EMF induced in it. Okay, so according to Faraday's law, the EMF induced is proportional to the rate of change of flux linkages. Okay, the EMF induced is proportional to the rate of change of flux linkages. So here E is the voltage or EMF, so it is directly proportional to the rate of change of flux linkages, that is d phi by dt. Rate of change of flux linkages nothing but d phi by dt. Okay, here phi is the flux, here d phi by dt is the rate of change of flux linkages. Here n is the number of poles, sorry, number of turns, and here n is the number of turns. This is the negative sign we are using. So E is equal to minus n d phi by dt. Here n is number of turns, phi is the flux, t is the time. Okay, so here assume that n is equal to 1, that is number of turns is 1, that means we have E is equal to d phi by dt. Okay, E is, assume that as n is equal to 1, that means E is equal to minus d phi by dt volts. So initially when the coil is moving parallel to the flux lines, already I said that no flux line is cut. Okay, initial condition when the coil is moving parallel to the flux, So whenever the coil moving parallel to the flux, there is no cutting of flux, and there is, if there is a no cutting of flux, that means there is no induced of EMF. Okay, that means d phi by dt is equal to 0 and E is equal to 0. Okay, d phi by dt is equal to 0. That means E is equal to 0. That is EMF is 0 for the first condition. So this vertical portion of the coil is the starting portion. I already said that. Next, after time t seconds, the coil would have rotated through an angle omega t. So after time t seconds, the coil would have rotated through the angle omega t radians in anti-clockwise direction. So here in this case, the flux then linking with the coil is BLB sin cos theta. The formula is E is equal to minus d by dt into BLB cos omega t, that is equal to EM sin omega t. Okay, that is the differentiation of cos omega t is nothing but sin omega t. Okay, from that one I am writing E is equal to minus d by dt of BLB cos theta. In the theta place I am replacing omega t. So that is equal to minus EM sin omega t. Okay. So when theta is equal to 90 degrees, that means, coming to the diagram here, so when the theta angle is 90 degrees, so when the conductor is rotated in the 90 degrees, at that time the coil sides are moving at right angles to the flux lines. Okay, the coil sides are moving at right angles to the flux lines. Here the flux lines are cut at the maximum rate. In this case, the flux lines are cut. Okay, the flux lines are cut at the maximum rate, and the EMF induced is maximum. So when theta is equal to 90 degrees, the coil sides are moving at right angles to the flux lines. The flux lines are cut at the maximum rate, and the EMF is induced is maximum. Okay, so when theta is equal to 90 degrees, the flux lines are cut. In this case, the EMF is induced at the maximum rate. So in the next case, when the theta is equal to 180 degrees, the coil sides are again moving parallel to the flux. So when theta is equal to 180 degrees, the coil sides are again moving parallel to the flux lines. That is, AB and CD have exchanged their positions. So AB and CD exchanged their position. That means AB is coming to this place and CD is going to that place. So that is, the AB and CD have exchanged positions, and the EMF is induced is 0 because the conductor, the coil sides are moving parallel to the flux lines. So at that time, there is no production of EMF. So there is no EMF induced in it. So that is 0. Okay. So again we are moving the coil sides at theta is equal to 270 degrees. 270 degrees. Here the coil sides again move at right angles to the flux. That means, but their positions are reversed. At that condition, the positions are reversed when compared with theta is equal to 90 degrees. So at 90 degrees, the coil sides are moving at right angles to the flux lines. Here also the coil sides are moving right angles to the flux lines, but in the reverse direction. Okay, in the reverse direction when compared with theta is equal to 90 degrees. In this case, hence the induced EMF is maximum in the opposite direction. So when theta is equal to 360 degrees, the coil sides once again move parallel to the magnetic field, making the induced EMF equal to 0. The coil has now come back to the starting point. Okay. So in this way, we are having this one. So I will show one diagram. So this one. So whenever the theta is equal to 0 degrees, at that position there is no cutting of flux. That means there is no EMF induced. That is, at that position the EMF is 0. I am indicating that this type. Okay. So when the coil sides are moving at theta is equal to 90 degrees, that means the coil sides are moving at right angles to the flux lines. So at that condition, the flux lines are cut at the maximum rate. Okay, that's why the producing of EMF is maximum at theta is equal to 90 degrees and theta is equal to 180 degrees. At that position, again the flux lines are not cut. That means the EMF is, the produced EMF is 0. Okay, and when theta is equal to 270 degrees, at that time same operation compared to 90 degrees, the coil sets are moving at right angles to the flux lines. Okay, here the flux lines are cut at maximum rate also, but in the reverse direction compared to theta is equal to 90 degrees. So here the maximum rate is occurred in the positive way, but here the maximum flux is occurred, maximum is occurred at negative direction. Maximum rate is occurred at negative direction, that is theta is equal to 270 degrees. And coming to theta is equal to 360 degrees. So here also the coil sets once again move parallel to the magnetic field. So here the making the induced EMF equal to 0. So here the magnetic EMF is 0. That is that the coil has now come back to the starting position. Okay. So this is the waveform regarding to the operation of the DC generator. That means conductor. Okay. Theta is equal to 0. The EMF is 0. That is there is no cut of magnetic flux because the conductor moves parallel to the magnetic flux. That's why there is no cutting of flux. There is no EMF is there. That is theta is equal to 0. And coming to theta is equal to 90 degrees. Here the coil sides are moving right angles to the magnetic flux. At that condition, the flux lines are cut at maximum rate, and EMF induced is maximum. So that's why the maximum value is occurred in this one. And again, theta is equal to 180 degrees. At this condition, there is no cutting of flux, and there is no production of EMF. At this condition, the EMF value is 0. And coming to theta is equal to 270 degrees. Here we have same compared to the 90 degrees. Here the coil sides are moving right angles to the flux lines. The flux lines are cut at the maximum rate, and EMF is induced maximum, but in the reverse direction. Okay, that is theta equal to 270 degrees occurred at maximum negative direction. And coming to theta equal to 360 degrees. At this condition, the coil sides are again moving parallel to the magnetic field. The flux lines are not being cut, and there is no EMF induced, that is 0. Okay, this is the waveform of the moving of the conductors. Okay, from one place to another place, from theta is equal to 0 to theta is equal to 360 degrees. Okay. Next, if the rotation of the coil is continuous, so that means here there is no stopping of the conductor. So that means if the rotation of the coil is continued, the changes in the EMF are again is repeated because the cycle is repeating. If the rotation of the coil is continued. Okay. Here I am showing that for the two-pole generator only, for the two-pole generator. Okay, shown one complete cycle of changes occur in one revolution of the coil. Okay, so that is the waveform I am shown. So here I am taking one commutator. This is the commutator. So why we are using the commutator means we have to convert the alternating quantity into unidirectional quantity, that is DC. For that one I am using the commutator. So here the EMF changes from instant to instant. Okay, from theta is equal at theta is equal to 0 degrees, the EMF is 0. At theta is equal to 90 degrees, the EMF is maximum. At theta is equal to 180, the EMF is again 0. At theta is equal to 270, again the EMF value gets the maximum value in the reverse direction. And at theta is equal to 360 degrees, the EMF is again come back to the starting position, that is 0. That means the EMF changes from instant to instant and becomes alternatively positive. And becomes alternatively positive, that is this way, that is become alternative to positive. This is the alternating. There is no flexibility of this one here. This is in alternating nature. That's why I am taking the sine wave. Okay, sine wave is the alternating quantity. Such an EMF is called as alternating EMF. Okay, such an EMF is called alternating EMF. And again, if the coil sides are connected to two slip rings, that is this one. So here the coil sides, if the coil sides are connected to two slip rings, this one A and B, these two are the slip rings. Okay, two slip rings A and B, and an external resistance R. This one is the external resistance, this one is the external resistance R. Okay, if the coil sides are connected to two slip rings A and B and an external resistance R connected across them, okay, connected across them, a current flows through the resistor. A current flows through the resistor. This is the current flow direction. So a current flow in the direction, okay. So which is again alternating. Okay, which is again alternating. So the induced EMF in the coil can be increased. So the induced EMF in the coil can be increased by using the two ways. First one is increasing the flux density, that is B, capital V, and increasing the angular velocity omega. Increasing the angular velocity omega. So here I will show this one. So here the current flowing in the external resistance to a DC generator is made unidirectional by replacing slip rings by split rings. So actually we are using the slip rings, but we have to exchange, we have to convert the alternating quantity into unidirectional quantity. For that one I am using the commutator, but here in the place of slip rings we are using the split rings. Okay, so the current flowing in the external resistance to a DC generator is made unidirectional by replacing the slip rings by split rings. Okay, so if we observe this diagram, I am P and Q. So P and Q is the two equal segments. So here I am separating the segments into two equal segments, P and Q. Okay, and the segments are insulated from each other. So these two segments are insulating from each other and also from the shaft. Okay, here we have two brushes, B1 and B2. Here we have two brushes, B1 and B2. These touches the segments. These two brushes touches the segments P and Q. Okay. P and Q, and likewise CD. Here we have, this is the insulation and these are the segments. This is the Q segment, this is the Q segment, P segment. Here we have two brushes. Okay, next I will show one more diagram. I will show one more diagram. These two diagrams. Okay, observe this diagram. First B diagram. So here the coil side AB. Here the coil side AB. This one. The coil side AB is always attached to the segment P. Okay, the coil side AB is attached to the coil side, segment P, and likewise CD segment, CD coil sides is attached to the segment Q. Okay, segment Q. So from this diagram, the coil side AB is connected to the P segment and the coil side CD is connected to the segment Q. Okay. Here the brushes B1 and B2. Here the brushes B1 and B2 touch these segments. P is brush 1 is touches to the P segment and brush 2 is touches to the Q segment and are meant to collect the current. Okay, these two brushes are used to collect the current. Okay. Next, during the first half revolution. So here, during the first half revolution, current flows along direction is AB. Current flows the direction AB, LM. So AB, LM, okay, and CD. AB. So the current flowing into the AB to the brush and coming to the L and M external load and going to the brush 2 and going into the CD. So this is the current flow direction. AB brush, next LM brush 2 and brush 2 to CD. That is the current flows along AB, LM and CD. Okay, through brush B1 which is positive and into B2 that is negative. This is the positive and negative. Okay, through brush B1 which is positive and into B2 that is negative. Okay, after a half a cycle, AB and CD have exchanged their positions. Here, observe this C diagram. Okay, observe this C diagram. Here in the B diagram, AB and CD is there, coil sides, but here in this case, it is interchanged positions. Okay, the coil sides are interchanged. In the AB place we have CD, in the CD place we have AB. Okay. Along with the segments here the segments are also changed. Here ABP, here AB also P, and here we have the coil sides is CD. Here the segment is Q. Okay, the coil sides are not changed. The segments are not changed. It is connected to AB side is connected to P, CD side is connected to Q, but only the coil sides are changed. Okay, along with the segments, coil segments PQ. Okay, here brush B1 is connected to Q segment and B2 is connected to P segment. If you observe this diagram, the Q segment is connected to B1 brush, and here the P segment is connected to the B2 brush. Okay, PQ. Here B1 is connected to P, B2 is connected to Q. Here in this case, B1 is connected to Q and B2 is connected to P. Why? Because here the coil sides are interchanged along with the segments. Okay. So for each half revolution, the positions of the segments P and Q also reverse. Okay. For each half revolution, the positions of the segments P and Q also reverse. Hence, the current in the load is always unidirectional. Okay. Hence, the current in the load is always unidirectional. Okay. The change over of segments P and Q takes place when flux linkage or induced EMF is minimum. So the change over of segments, here the segments are changed PQ to Q2P, P to Q to Q2P. Why? Because it takes place when flux linkage or induced EMF is minimum. So when flux linkage or induced EMF is minimum, the segments PQ are interchanged. Okay. So in a generator, the split rings are called commutator. The split rings are called commutators. So this is the diagram. This is a unidirectional diagram. Okay, 0 to maximum and 0 and 0 to maximum and 0 in only one direction. So in the previous we are having positive and negative peaks, but here we have only positive side. So if you observe this, we have positive and negative directions, but here we have only the positive direction. Okay, only one direction, that is the unidirectional. Okay, I'm stopping here.